So, I had introduced the concept of angular momentum, and even for a single particle this is a useful concept. Together with linear momentum and energy, angular momentum is another physical quantity which is very useful in dynamics. How do we define that? We define angular momentum L of a particle and about an origin. These things are important. About a chosen point which we call origin, and the definition is this L is equal to R cross P. What does that mean? You have an axis system, you have an origin, you have the particle somewhere here, and then the particle may be moving in some direction, its mass is m. At that instant, what is the position of the particle as seen from this origin, from this frame of reference? That is known as r vector, r, this r vector, and p is the linear momentum, the mass of the particle times this velocity. So, that is it. And then similarly we define torque. This also on a particle. So, these adjectives are important. Of a force, we call torque of a force, and force is acting on some particle, and once again about the origin. So, this is important, and then we say that torque is R cross F. This R is same as this R. This is the position vector of the particle on which this force is acting, and this position vector is taken from the same origin, and then we call this torque about that point. And then you have a very simple relation that torque is equal to dl dt. Simple. L you know, so dl dt if you do, it will be differentiation of the first function cross the second function as such, and then first function as such, and differentiation of this second vector. Now, it is important that the order is not changed, R first, P next, R first, P next, R first, P next. So, this order should not change, and then one sees that this is 0. Why? This is parallel to velocity, this is velocity itself. So, this is 0, and this is force, resultant force dp dt, and therefore, this is equal to tau. Simple. Now, let me take a very common example, simple example, a particle freely falling under gravity. So, it is dropped, a particle is dropped, and then it falls. So, it falls on a vertical line, and then it reaches ground. So, it is dropped from here, and we can take the origin right here, and then x axis, y axis, and z axis, and if this time is t equal to 0, at certain time t, it will be here. So, this is at time t, and this distance is half gt square. So, if I ask what is the angular momentum of this particle at time t, so L at time t, this is r cross p. Now, what is r vector? Here is the origin. So, this is our r vector, this is our position vector of the particle at time t. And what is the linear momentum? It is mass times velocity, and the two are in the same direction, r vector and this p vector are in the same direction, and therefore, this is 0, angular momentum remains 0, it moves on this straight line. And torque at time t, r cross f, that also you can work out. What is the force? The force is mg. The force is F is mg. Which direction? Vertically downward. So, once again R and F are parallel to each other and therefore, it is 0. So, obviously, torque is dl dt. L is 0 all the time, torque is 0 all the time. So, torque is dl dt is obviously correct. If you take your origin here, same story, same story. This is r vector, this is r vector then, and this is f vector, and this is p vector. So, same story. What if I take the origin somewhere here? Let us say this is a point O, and this is point A, and this is point P, and my origin is here. Now, what is the angular momentum? Is it 0? The angular momentum L is r cross p, and r vector is from the origin to the particle. So, this is r vector. So, this is r vector. So, OP cross product with p vector, mass times velocity. What is velocity? GT. If I call this let us say this is x axis, this is y axis, then it is velocity is GT in minus k cap direction, minus j cap direction, right. Velocity is g into t, v equal to u plus gt, u is 0 and therefore, it is mgt, mass times velocity, and then the direction of the velocity is in minus j cap direction. And if I work it out, this OP vector is OA vector plus AP vector. So, it is OA vector and plus AP vector, and cross mgt and then minus j cap. OA, this is x direction. So, let us take origin here, and this is our x direction, this is our y direction, and the z direction is here. So, this was earlier. All right. So, this is origin, this is the OP vector, and which I am writing OA plus AP. OA is this distance is some distance OA. So, this is OA times and I cap plus AP. So, it is AP and times this what j vector and cross mgt minus j cap. So, j cap cross j cap is 0, but I cap cross j cap is not 0, it is k cap. So, this is OA multiplied by mgt and then minus, and I cap cross j cap is k cap. All right, OA is fixed. The particle falls like this. So, all the time OA is fixed. So, OA has a magnitude, depends where you have chosen the origin, and then mgt in minus k cap direction, and k cap, remember, is now perpendicular to the blackboard. So, the particle is falling along this parallel to this y axis. This particle is falling parallel to the y axis, but its angular momentum is in z direction, negative z direction. If this is x, this is y, z is coming towards us, and minus k cap means it is going into the board. So, that is L. What is torque? Torque is r cross f, and r is OP vector. So, OP cross f, f is mg in the downward direction. So, mg times minus j cap. So, minus j cap, Look at this expression for L and this expression for torque. What is the difference? OP cross mgt minus j cap, OP cross mg minus j cap. Only this t is not there, otherwise everything is there. So, now if you do this dl dt, here is dl, this is here is L, this is L, and I am doing dl dt, differentiate this with respect to time. OP is a fixed vector, no, OP is not fixed vector, OA plus AP, you can write it like that. So, your dl dt, if you take from here, OA is fixed, correct, OA is fixed. So, this is OA and then mg is fixed and differentiate with respect to time. So, it is 1. So, it is minus k cap. So, OA into mg and then differentiated here minus k cap. And what is this? This also you can work out. This is OA plus AP and then cross mg and minus j cap. And once again AP is parallel to this y axis. So, this part will go away and what you will have is this OA and then mg here, m into g here, OA here, and this OA is in x direction. So, x I cap and j cap is k cap. So, minus k cap, simple. Same as this, torque is same as this dl dt. So, even for a particle which is falling vertically under gravity, if the origin is chosen in a certain way, you do have angular momentum, you do have torque, and then the rate of change of angular momentum is equal to torque, that equation is valid. So, my next example is from central forces, and we will be talking at length about the central forces here to introduce this idea of angular momentum and its use. So, we call it central force because you have a force center. So, you have a point and the particle is can be anywhere, and then the force on the particle is always along the line joining the particle from this fixed point, that we call force center or center of force. So, you have a fixed point, the particle can go anywhere in the whole space, but wherever it is, you join the origin with that position of the particle, the force on the particle will be along that line, either towards the center or away from the center. And then the magnitude of the force depends only on this distance from this fixed point. If that happens, we call that force as a central force. So, I can write for central force F at r is equal to some function of r without vector. Okay? Here r is with vector, here r is without vector, and then r cap. What is r cap? Just tell. First, let us see what is this r vector and what is this r. R vector is, as usual, position vector of the particle at time t. So, at time t, the particle is somewhere and I join the origin and the particle, and that vector is this r vector. Force on the particle when it is at that position, that is our left hand side. Okay. Force on the particle when the particle is at this position, So, that is the left hand side. And what is the right hand side? It is the distance of the particle at that instant from the origin. Here is the particle, here is the origin, and this is the distance, and that distance is r. And this direction is the direction of the force. Okay. It need not be in general, it need not be in this direction, but for a central force it has to be in this direction. This r cap vector is along this line, and in the increasing r direction, unit vector along the direction of this position vector, this is known as r cap. So, this Fr, if it is positive, then the force is away from the center of force. If this Fr is negative, then the force is towards the center, attractive or repulsive. So, we have enough examples for such central forces, at least approximately our planetary system, sun and the planets. So, sun attracts the particle, the planet, wherever it is. So, the force is in the direction of that sun, that means opposite to the position vector, and the magnitude depends only on the distance between the sun and the planet, right. The sun is given, the planet is given. So, m1, m2 is there, capital G is there. So, it is only by r square, it depends only on r, not on the direction, not on the direction. So, or let us say Bohr's model of atom, you have a proton and you have an electron, and then in that model the electron is supposed to go in some circular path. So, all the time the force on the electron is towards that proton, which is taken as the origin, and the force depends on the distance only, q1 q2 by 4 pi epsilon naught r square. So, you have so many examples. Okay. So, let us try to study this. Now, suppose this particle is acted upon by this central force, and we ask what is the angular momentum of the particle. How do I write the angular momentum of the particle? So, first let us take some axes, and in this process I will be telling you more about another coordinate system in 2 dimensions, which is known as plane polar coordinates. So, I have x axis and y axis, and then the particle is somewhere, and if I join the position of particle from the origin, this vector is the position vector r, and the unit vector along this position vector is known as r cap, and then this angle I can call theta, and if you do not increase the distance, but turn it, so that this theta increases. So, in the direction in which r is not changing, but theta is increasing, that means perpendicular to this. This direction is known as theta cap direction. So, if I take the particle in this direction, this theta will increase. If I take it infinitesimally small distance here, this theta will become theta plus d theta, but r will remain the same. Same means if it is infinitesimal small, okay, there is no component of that displacement in the r direction, and therefore, for that infinitesimally small displacement we will take that r is constant, only theta is changing. This is r cap, this is theta cap. And if I drop a perpendicular here, this is x and this is y. To get the position, I can write what is x and what is y. I can also write what is r and what is theta. If someone says that all right, it is at a distance of r from the origin, and this line makes angle theta with the x axis, that also tells me that okay, the particle is here, provided the particle remains in this xy plane. If it is in the xy plane, yes, give me r, give me theta, I know that it is in this plane and I know where the particle is. If I know that it is in xy plane, give me x, give me y, I know that it is in this plane, and here is x, here is y, and this should be the particle. But if it is leaving this xy plane and it moves in a space, 3-dimensional space, z is also there, then neither this is sufficient nor that is sufficient. Let us come back to our angular momentum. So, angular momentum of this particle at time t is given by L equal to r vector and cross p vector, that is mass times r and cross v, and torque. Torque is tau, which is dl dt of course, and which is r cross f. Now, here is the crucial point, r cross f. This is vector r, and the force is also along that direction, r cap. The force is either towards the center or away from the center, but it is on the same line, and therefore, when you do this r cross f, this is 0 for central force. And if torque is 0, that tells me that this L is constant, and remember, it is d dt of L vector. So, if that is 0, that means L vector is constant, and L vector is constant means what? This is constant, this is constant. L vector is equal to mass times r cross v, and this is constant in magnitude as well as in direction, and this is a constant vector, remember, and this v is perpendicular to, this v is perpendicular to L. That is how the cross product is defined. The cross product of two vectors is perpendicular to each of these two vectors. So, L is perpendicular to r, L is perpendicular to v. I am interested in the second part. L is perpendicular to v. So, v is perpendicular to L, and L is a fixed vector. So, particle does not have any component of velocity along this direction, this L direction. If I call this L direction, as z axis, v is always perpendicular to L, that means v is in xy plane. That means Vz is 0, no component in z direction. So, if initially there is no component in z direction, and then you cannot pick up any magnitude of that, it has to remain in xy plane. So, the way you start, how you start in this direction or that direction or that direction, that will decide finally the plane of motion, and the particle must move in a plane. Okay. So, does not matter what this function is, 1 by r square, 1 by r cube, whatever, all right. The motion of the particle is in a plane, all central force motion is coplanar, in one single plane it remains, and therefore, we can use this. Right. Therefore, we can use this, and let me go little ahead of this. What is this r cap in terms of I cap and j cap? Remember, this r cap and theta cap, they depend on where this point is. If the point is here, r cap is in this direction, theta cap is in that direction. These are not constant vectors, they depend on the position of the particle. I cap, j cap are constant, x axis is fixed, y axis is fixed, particle is moving. I cap, j cap are constant vectors. So, I can write this r cap as cos theta I cap and plus sin theta j cap. Verify, this angle is theta, this angle is theta, and so this is unit vector, cos theta this component and sin theta that component. And theta cap if you write, so it has one component this side, one component that side. So, minus sin theta I cap and plus cos theta j cap, that is theta cap. Now, very interesting, what is dr cap dt? And first, what does this mean, dr cap dt? The particle is here, you have a r cap direction, this is r cap. Then in a time dt, the particle goes from here to somewhere else, let us say here, of course, in time dt. So, it is infinitesimal displacement, and now r cap is this. So, how much is the change in r cap? This vector and minus that vector, that is change in r cap, and therefore, I divide by dt and I get this dr dt. Okay, so here is r, these are fixed vectors I cap, j cap, theta can vary, theta is variable, theta can change as the particle moves. So, this is minus sin theta and then d theta dt and plus cos theta and then d theta dt, here is j cap, here is I cap, and this is minus sin theta I cap plus cos theta j cap and theta dot, and when I write dot it is d dt of theta, and this is theta cap, this is theta cap, theta dot, it is theta dot theta cap. So, dr cap dt is theta dot and then theta cap, right. So, once again let us write this L vector. You can write what is V vector. What is first R vector? R vector is R cap. Can you see this? Can you see this? R vector is R, that is the magnitude, and the direction is R cap. So, R vector is this magnitude R, R cap. So, what is dr dt? Dr dt, this is the velocity of the particle. This is the velocity of the particle, dr dt, r vector here. So, differentiate this, keep this as constant, then keep this as constant, differentiate this, and that is equal to r dot r cap, then plus r times dr dt. Dr dt is right here. So, it is r and then theta dot and then theta cap. So, the r component is r dot and the theta component is r theta dot. You can write it like this, and you can write an expression for this L, which is m times r vector cross v vector, and r vector is r cap, and then cross v vector is here, v vector is here, r dot r cap plus r theta dot theta cap. R cap cross r cap is 0. So, it is m into this r and then theta dot r cap cross theta cap. Come back here. Here is r cap and here is theta cap. So, what is r cap cross theta cap? This is a unit vector in this perpendicular direction, and that is z direction. So, this is k vector, unit vector k cap. So, this is k cap. Okay. So, we have already shown that the whole motion is in xy plane and angular momentum is taken in the z direction. So, that comes out in z direction, very good, very nice, and it is fixed, direction is fixed. Magnitude is also fixed, L vector is a constant vector, and here is the magnitude. So, L is equal to m into r square into theta dot, and this is constant, means r square into theta dot is constant. This particle may go somewhere in this plane, r is changing, theta is changing, theta dot is changing, but r square theta dot must remain constant. So, we will take it from here, we will talk much more about central forces.